Okay, hello and welcome to your first reading assignment for the year, the first of many. It's Unit 1, Astronomy, and it's on the Sun. And this discussion will correspond directly with your reading assignment. It's Chapter 26, Section 1, the Sun, pages 832 to 37. Really going to try to focus on those key points that you see at the end of the chapter. Obviously, we're all somewhat familiar with the sun. We know that it can be harmful to us, and we wear sunscreen to protect against that. And we probably know that it provides energy to planet Earth and basically is the engine for all life on our planet. But before we get started with the sun itself, I thought a couple of things might help to give you some perspective. Obviously, the sun is the center of our solar system, but you may not know that it actually accounts for 99.8% of the mass of the entire solar system. So this model that you see here on the screen is obviously not to scale, both in distance or size. The sun is very large in comparison to the other planets and objects that are inside our solar system. The temperature you see there is in Kelvin, 5,800 degrees Kelvin at the surface, which is about 9,980 degrees Fahrenheit. So it's quite hot, and it's even hotter at the center, 15 million degrees Kelvin at the center. It is a glowing ball of gas, and it's roughly 70% hydrogen and 28% helium. And we're going to see that ratio consistent throughout the universe. It's something we'll be talking about as evidence for the Big Bang Theory. Finally, the sun provides a tremendous amount of energy, as I said before, and it does this in the form of electromagnetic radiation. Here is a diagram of the electromagnetic spectrum, and there's quite a lot going on here, so it may look overwhelming at first. It is something we're going to look at quite a bit throughout the course of the year. But for now, let's just look at this sort of in chunks. On the top of the diagram, you see wavelength. And you can see that as you increase wavelength, as the wavelengths get longer on the right side of this, that they in fact carry less energy. And the opposite is true. As the wavelengths become shorter on the left side of that diagram, you see that those waves carry far more energy per wave. And so if you've been to the dentist and you've had an x-ray taken, you know that hopefully they put a lead vest over you to keep your organs safe from the x-rays that they're using to examine your teeth, because they could be harmful to the rest of your body. And maybe if you're a beachgoer in the summertime, you know that UV rays, ultraviolet rays, actually can burn your skin. That's what causes sunburn. You may not know, though, that in fact radio waves are all around you, bumping into you all day long, and you don't feel them, and they don't infect you in any way. So, and again, the center portion of the spectrum, or of the diagram, excuse me, lines up with the wavelength on the top. So radio waves on the right side are longer and carry less energy, as opposed to gamma rays, which we'll talk about very soon here, coming from the sun, which are very short wavelength and high energy. Also notice on the bottom of this diagram that we have the visible light spectrum, the light that you and I can see, that our eyes can process and understand. It's only a very, very small portion of the overall electromagnetic spectrum. Once again, we'll be coming back to this quite a bit throughout the course of the first semester. Okay, so we know that the sun produces a tremendous amount of energy for planet Earth and for everything else in our solar system. So how does that happen? Well, the short version of that is that nuclear fusion occurs at the core of the sun. As you can see in the diagram below, what's going to happen is that two hydrogen nuclei are going to be pushed together so tightly that they in fact will fuse into one and form a new element, and that element is helium. And when that happens, energy is released, as you can see by the gamma ray in the diagram. So gravity in the sun is pulling all of the hydrogen towards the center, towards the core. And at the core, pressure and temperature is so high that fusion is able to occur, therefore releasing energy. Okay, we're going to study gravity quite a bit throughout the course of the year, but for right now, just understand that the more mass an object has, the greater its gravitational pull. And the sun's quite large, and all stars are, so that's good for the star, especially considering, as we said on the last slide, that there's a great deal of outward thermal pressure that is created by the fusion of hydrogen atoms into helium atoms at the core of the sun. And so for about 5 billion years now, the sun has been fusing hydrogen, and it's experienced this outward pressure, and gravity has been able to maintain that balance and keep the sun fairly stable. We expect that to continue for roughly another 5 billion years. At that point, we're not really sure if it will have enough energy to continue fusion, and the sun may cease to exist. Okay, so the sun's interior consists of the core, the radiation zone, and the convection zone. And your textbook on page 834 has a diagram of this. We'll look at another diagram towards the end of this presentation. The core is roughly 1/4 the size of the sun's diameter. That's where nuclear fusion occurs. The radiation zone is an incredibly hot and incredibly dense layer of gas, highly compressed gas. And energy from the core, from the fusion that occurs in the core, is transferred by the absorption and radiation of electromagnetic waves. And because of the density of this region, it can take that energy up to about 100,000 years to actually pass through it. Once that energy gets to the surface of the sun, it only takes about 8 minutes for it to get from the sun to Earth, just to give you some perspective. The outer layer of the sun's interior is called the convection zone, and here energy is transferred outward by convection currents, something we'll be talking about more in class. Okay, I'm sure you all know that Earth has an atmosphere, and that's where weather occurs. And you might be paying attention to that right now, as hurricane season is upon us. But the sun has an atmosphere as well, and it consists of 3 layers: the photosphere, the chromosphere, and the corona. The photosphere is what we consider to be the sun's surface. It's not a solid surface, as you can see here, and that's where we get that temperature reading of 5,800 degrees Kelvin. It's roughly 500 kilometers thick. The middle layer is actually hotter. It's called the chromosphere. So again, these are moving out. The photosphere would be the lowest layer in the sun's atmosphere. The chromosphere is the next layer. The corona is the outer layer. The chromosphere is, well, as you can see here from the text, it's so hot that the hydrogen gas there actually emits a reddish light at that temperature. And finally, the outer layer is the corona, and that extends millions of kilometers above the chromosphere. And it sort of gradually turns into this solar wind, which is a stream of electrically charged particles that are flowing from the sun outward. Now, in the picture in the background, you can see Earth, and you can see these sort of blue lines. Those blue lines represent the magnetic field of Earth. And fortunately for us, the magnetic field of Earth actually deflects a lot of those electrically charged particles that would otherwise be harmful for us. And finally, we're going to look at 3 features on or above the sun's surface. The first of which are sunspots. These are areas in the photosphere where gas is cooler than the surrounding areas. Sunspots are not small. In fact, some are larger than Earth. They also are not really all that dark. They appear dark because they give off less energy than the surrounding photosphere. They're often found in groups and are associated with intense magnetic fields on the sun. The number of sunspots actually varies, and there are peaks and troughs associated with this. Prominences are huge loops of gas that erupt from the sunspot regions, and they can reach heights of 100,000 kilometers above the sun's surface. The sun's surface sometimes erupts dramatically, producing X-rays and hurling charged particles into space at speeds of 1,000 kilometers per second or more. This sudden release of energy is a solar flare, and it can heat the corona to temperatures nearly 20 million degrees Kelvin and greatly increase the solar wind. That can actually cause magnetic storms in Earth's upper atmosphere and disrupt electric power transmission as well as radio, television, and telephone signals. And lastly, I wanted to give you these 2 diagrams. They both show the same information, but they present it slightly differently. You could certainly pause this and you could take a picture of that, or you could. I would recommend, if you would like, to actually just draw this out in your notebook. For me personally, I know that if I create a diagram or I draw a picture, sometimes it's easier for me to remember the information that's contained within that. Okay, well, that's it for today. Thanks so much for watching. If you have any questions, ask them in class. We'll see you then. Bye.